Nuclear binding energy refers to the work required to separate nucleons and overcome the strong nuclear force. It also refers to the amount of energy that is released when a nucleus is formed from the nucleons. It has a short range of about 10 to the negative 15 meters.
The mass defect is the mass equivalent of the nuclear binding energy, or the difference between the masses of the nucleus and the nucleon is known as mass defect. The mass defect is essentially a measure of the binding energy.
In the occurrence of a nuclear reaction releasing energy, the products are in a much lower energy state compared to the reactants, which can only mean one thing. The difference in energy states is a result of mass loss.
The binding energy in a nuclear reaction can be determined through Einstein's equation E equals mc squared.
The E represents energy, m the equivalent mass, and the variable c represents the speed of the electromagnetic waves in a vacuum. Nuclear binding energy is generally larger as the size of the nuclei increases and becomes much harder to separate as there are more nucleons for the strong force to interact with.
The average energy per nucleon can be determined by finding the quotient between the total binding energy of the nucleus and the number of the nucleons. Looking at the graph of average binding energy per nucleon compared to the nucleon number, the binding energy is much weaker towards the left, meaning that the nucleides are less tightly bound compared to the larger nucleides.
The average binding energy per nucleon reaches a maximum binding energy as the graph reaches the center, where the nuclides are the most stable and abundant. As we move more gradually to the right, the binding energy decreases with the heavier nuclides, making them less tightly bound. Going furthest to the right, where heavy elements like uranium and plutonium have 1 mega electron volt less binding energy than the center region.